Hi, and welcome to this talk. So I will be telling you. So my name is Küngas. I'm the CTO and co-founder of Stargate Hydrogen. But today I will be telling you about one quite exciting European project which we are coordinating, which is about improving alkaline electrolyzers. So that we wouldn't be in this, have this kind of relatively poor performance that was shown by the previous speaker. And we will do this by special electrodes, which are called flow-engineered three-dimensional electrodes. But I will tell you a lot more about what this is. So the ENDURE project is a project funded by the European Clean Hydrogen Partnership, and it includes multiple partners. So electrode development is done by Fraunhofer EFAM from Germany. We, Stargate Hydrogen, are the coordinators of the project, and we are doing stack development. The Aragon Hydrogen Foundation is doing stack testing in the project. Permascand is an industrial partner specializing in electrode design. ZSW from Stuttgart is helping us with accelerated stress tests, stack tests, and material development. UC Louvain from Belgium is also carrying out testing and working on some of the modeling tasks. So we have a really nice consortium for this project. Overall, it's a 3-year project, and we're at the moment roughly halfway through the project. But let me then jump directly into what this project is all about. So if you think of alkaline technology, then most of what is talked about is this really old, what we call there on the slide, Gen 1 technology. You have a finite gap structure, you have 2D electrodes, so just metal plates, and you don't have what we call like a porous transport layer, so no kind of flow pattern inside the stack. And so these kind of cells were really popular in the 1950s, but things have moved on since then. So Gen 2 is what is called like a zero gap design. So still you would have plate electrodes, but now the electrodes are very close to the diaphragm. And recently what has emerged is Gen 3. So where instead of those 2D electrodes, you now include 3D electrodes. So this can be your nickel foam, maybe felt structures like that. And where the main innovation of this project then comes in is combining the zero gap design with 3D electrodes together with a flow-engineered porous transport layer. So let me tell you more about it. But first, let me tell you why this seems to be a good idea. So just recently, one of the partners of the project, UC Louvain, published this paper in Nature Communications, which shows that if you combine these like a bilayer nickel foam structure with a good catalyst in the fine layer, you can achieve really they call this PEM-like performance. So we're talking about 2 amps per square centimeter at 1.9 volts per cell. So this is really like a step change in the performance of alkaline technology. And then in this project, we're developing this concept further by essentially optimizing the structure of this porous transport layer behind the electrodes. So what does this mean in practice? Let me show you some examples. So the electrode structure will now consist of multiple layers. So you can have like a really rough first layer consisting of large pores, second layer with smaller pore size, maybe around 500 microns in size, and then finally a really fine catalyst layer which is kind of touching the diaphragm. And we have been successfully manufacturing these layers. You can see some examples here. This work has been done by Fraunhofer. And some of the results I will show you here. So first of all, let's look at the layers or the performance of layers without the final catalyst layer. So some performance curves are shown here. You can see that, well, first of all, the performance is reasonable, but without a catalyst, it's not yet super good. So we're getting at around 2.1 volts at 1 amp per square centimeter. But another thing to pay attention to is this flow effect. So you have exactly the same electrodes, but by ramping up the KOH flow rate in the cell, we're able to really decrease the energy consumption of the reaction. So, and we have done quite thorough analysis of this, and the extra kind of energy that you have to put into pumping is still significantly less compared to the energy gain that you get from this flow effect. Yes, so, but let me explain to you what this flow effect is all about, because this is kind of a key concept in the project. So if you have this bilayer structure with a coarse layer on the outside and a fine nickel layer in the inside, and then you have this upward KOH flow from the bottom, then what will happen if you have this particular structure is you will get this red curve. And what this red curve tries to tell you is that in the direction from this purple layer towards the black and white coarse layer, you will have a directional flow. So kind of in the direction that the arrow is pointing, the red arrow is pointing. So, and this kind of preferential flow you only have if you combine a fine mesh, a fine foam with a coarse foam. If you combine the fine foam with a knit mesh structure or the kind of simple elastic element structure, you don't get this same kind of preferential flow effect, which is shown by the blue curve. So it's really kind of something special and shows that there's this entire area of electrode design which up to now has not really been addressed. And in other words, we can teach this old technology of alkaline electrolysis a lot of new tricks and improve its performance quite a lot. So let me show you now the first results of what we can get when we then add catalyst coatings on the electrode. So yeah, so now the graph is similar, but the structure now also includes the orange layer on top. So we have added a catalyst layer and tested under exactly the same conditions. And by doing that, we can decrease the energy consumption of the cell to 1.9 volts at 1 amp per square centimeter. So still very high current densities for alkaline technology. Yeah, we're not done with the catalyst development, but I would like to show some results. So, for example, as the cathode in this project, we're using nickel molybdenum catalyst. You can see the structure on the photo there. And this is something that has been developed by the Fraunhofer Institute. And they have also carried out, yeah, I wouldn't call it long-term testing, but to demonstrate that this this electrode might also work long-term. So in this 100-hour test under industrially relevant conditions, 30% KOH, 80 degrees, 670 milliamps per square centimeter, we're getting really very nice and low voltage values at around 1.6 volts. Yes, and yeah, we're not really stopping in this project on cell level. We are actually quite a lot of work is also happening on stack level. So we're doing really comprehensive, like micro scale, but also stack scale modeling of the of the entire stack. So which includes like flow patterns, pressure drops, shunt currents, gas volume fractions, and so on. And many of those results we will be sharing as the project progresses. And we're also doing stack testing. So here's one example of a stack that was assembled as a part of the project, and which is presently being tested at ZSW. But many more tests will come. So in this 1.5 years, what have we achieved? We have successfully developed flow-engineered 3-dimensional electrodes, as I showed, and showed that they can, as a matter of fact, result in excellent performance. We have, on cell level, achieved 1.9 volts at 1 amp per square centimeter with completely PGM-free electrodes. And this flow effect that I tried to explain in a little bit more detail, we have shown that it is real, and this is kind of what is really boosting the performance of our cells and stacks. We are doing quite a lot on stack testing and stack modeling level. We will be telling you much more about that as the project progresses. So yeah, we're still more than 1.5 years. There's 1.5 years more to go in the project, so you will be hearing much more about this. And if you would like to know more, or then please come to visit the Stargate booth, which is at exactly the other end of the exhibition in booth C122 for more information. Thank you for listening.